Okay, so we can resume. Thank you. So welcome to the third talk of the afternoon, which is the last in-person talk of the day and of the workshop, of course. We have that is the right thing to say now. I need to die. Oyunchimeg?
Yes.
Oyunchimeg, SHAGDAR. From VEDECOM. Based in Paris, is correct? VEDECOM is
VEDECOM,
yes. So Dr. SHAGDAR is senior researcher at VEDECOM Institute and also research team leader. She obtained a PhD degree in information science and control engineering in Japan, at Nagaoka University of Technology, a few years ago, and then she got the qualification in France, the HDR qualification, and moved back to France, to Versailles at the beginning, so next to Paris. Her research interests include wireless communication, cybersecurity, quality of service. So today we're going to have a sample of what she's doing related to V2X. And so thank you very much for being here, and the floor is yours for the talk.
Thank you for the introduction, and thank you so much for organizing this workshop and inviting me for a presentation. So, this work, I will present today message redundancy and congestion control for V2X collective perception service. So the work has been done with my PhD student Amine Shtourou and my colleague Pierre Meldignac from VEDECOM. Okay, so we can change, yeah. So I think we have already talked a lot about automated cars. So still I need to start a bit there. So what automated car is a robot, right? So it basically do three things: sensing, planning, and action. So as we see, the sensing or perception part is the fundamental part of the system. And for autonomous cars, as it is, they use tons of different types of sensors, touch sensors, vision sensors, in order to really perceive the environment. What they need to perceive, they detect the road marking, they need to recognize the lanes, the different panels, vertical, the panels, traffic lights, and they also need to detect the different types of obstacles, which is very important for the collision avoidance. So they need to detect obstacles, classify them. So vehicles, cyclists, pedestrians, or even just one box or something on the road. Whatever obstacle is, they need to detect them. We all know that there are a lot of difficulties there because the sensors are basically quite very strict line, and they requires line of sight in a situation. So as soon as there's obstruction, it cannot detect the object behind there's something that obstructs the vision. And also it's extremely dependent on environmental condition, especially it's true for the vision sensors like our eyes, that as soon as it's night, we don't see any. And there's also some limitations in terms of coverage and so on. And this situation is also especially difficult in certain scenarios, like at intersections or at highway entry-exit points, or some bus stations, of tolling areas. There are tons of situations we can imagine that local sensors will not work. So there we are talking about V2X communication, how V2X communication help that the vehicles to have extended perception. So V2X communication, Thierry gave a good presentation on standardization activities. So basically for V2X communication, whether it's vehicle or infrastructure or other central entities, they need to have some, they need to have this CITS protocol stack there. So I'm not going to talk about the protocol stack itself there, but there's a one so-called facilities layer, which basically generates important information and disseminate, help transmit this information, and then also receives this information and put in local dynamic maps so that application can analyze and finally perceive the situation. So this is in the facilities layer. There are different types of messages already can be can be generated and transmitted there. But for the perception, extended perception point of view, there are two types of messages, very important. One of them is, first of all, Cooperative Awareness Message, which has been standardized 2011, many years ago, which requires basically all the connected vehicles, basically vehicles, periodically inform their presence. So I am vehicle, I am at this place with this speed, with this direction, and so on, so on. So this is quite good, but the problem is obviously not all the objects can communicate, right? So there are now the second message, which is called collective perception message, which has been mentioned several times yesterday and also today, is basically to help to even there's objects not communicating, we still need to inform the presence of these objects. And so this has been a collective perception message can be generated by vehicles of infrastructure that are equipped with sensors. And this collective perception message is basically consists of different containers. So there's a header and so on, obviously. But the important part is that it describes the what kind of sensor it used, what is the field of view of sensor, and so on. But most importantly, there's a perceived object container. In the perceived object container, it says for each perceived object, it says this object is at this position. I think this is this type of object. Maybe it's a car, maybe it's bus, maybe it's truck. I think this is the velocity is this, and it's talking about its perception. So there's not, yeah. So and then there are if it detected n number of objects, we will have n containers of the perceived object containers. Yeah. So like I say, that any vehicle infrastructure that are equipped with sensors can help for collective perception. Then we can still think of, okay, we have roadside infrastructure that are equipped with sensors. And if we have vehicles also equipped with sensors, both of them communication capabilities. So we want to compare this to what is the capabilities of infrastructure versus vehicle. So we can easily say that roadside sensors can be installed in such a way that field of view is larger and it has less obstruction issues. Normally the antenna is higher, so the communication coverage is higher, larger as well compared to vehicle. Obviously, computing capability is higher there. So we are question there is that having this in our mind, our research question is that, okay, let's say everybody is sending CPMs and vehicles and infrastructure sending CPMs, what happens at the receiver side? So basically, just imagining in this very simple scenario, we have a go vehicle which is equipped with sensor, which is detecting a vehicle in front of it. There's a roadside sensor sending CPMs. Eventually another vehicle sending comm message or something. Then already in this simple scenario, there's a redundant information coming from the receiver side. So if you imagine the real scenario, lots of vehicles and so on, at the receiver side, there will be too much data, potentially too much data to process. That means there will be higher processing overhead, maybe eventually leading to perception error and so on. And also there will be increased channel load. There's a lot of redundant information unnecessarily using the wireless resource, which is not unlimited. And so what we're interested in is that, okay, we want to study the impacts of vehicle versus infrastructure roles for the collective perception and propose eventually CPM content selection and transmission control mechanism. Because like say in this case, if the roadside, if the vehicle receives the redundant information, maybe some of these infrastructure vehicles maybe decide to not send unnecessary information. So that's the content selection and transmission control. So this is our motivation. So first of all, we
Now
start.
let's move to our first contribution, the analytical model that we proposed. So
Okay,
let us
sorry about
imagine
this.
the scenario.
I have a. I need to. I didn't try this one. Voilà. So this slide has been used for another. Are you seeing good one or not? This one. Yeah. Okay. So first of all, we start with the analytical model. So we did very simple analysis. So we imagined the three highway, 3-lane scenario, and we have this blue vehicle, which is having 360 degrees of sensor. And then we say, okay, how many objects it can detect? Okay, that's what we're interested in. And then if there's a roadside unit next to it, how many objects roadside units can detect? So that's what we're interested in. Then for that, we need some assumptions. For example, for vehicle, we say that, okay, it will have obstruction issues. So on the same lane, it can detect only the vehicle right in front of it or the behind of it. But on the parallel lane, it can maybe detect several vehicles, but we are interested in how many. On the roadside unit, for the roadside unit, we said, okay, let's say a roadside unit can be installed in such a way that there's not much obstruction issue. Okay, so then now in this scenario, what we are basically interested in is that how many perceived object container vehicle will put in CPM and how many perceived object container RSU will put, roadside unit will put. So we are interested in basically the N, right? N in the of the CPM. Then we have this simple geometrical calculation, and we find out, okay, N for vehicle is this, N for roadside unit are this, okay? Here the max is the coverage, sensor coverage of the vehicle when if it's line of sight. Based on that, what we get, if you put that in graph, we will have quite interesting results that on horizontal axis, we increase the density, vehicle density, number of vehicles per kilometer per lane. And we have red one is the number of, on the left side, first of all, number of perceived vehicles for vehicle, okay? So in the beginning, it will perceive around 6. Then as soon as the density increase, it will go to up to 10, and then that's it, no further. Then when density becomes too dense, then it will drop back. It will not go, it will not stay at 10. But for a roadside unit, as our assumption is okay, there's no obstruction issue and so on, it will the number of perceived objects will increase with the increase of the density. Now, if in reality, for the communication point of view, have this data frame size.
Now we are interested in calculating.
Sorry, encore, I have to remove this. I should have checked this before.
You can mute your audio, the audio of the computer. Maybe.
Okay.
No, you check it. It's still, I check it. We still hear it.
Okay. Again, I go to the. I'm sorry about this. So if you check the CPM length, actually, unfortunately, a roadside unit cannot put all the objects because there's the size limit for the technology coming. So, for example, if you say 1,500 bytes for Wi-Fi technology that we imagine here, then it will basically put up to around 60 something number of objects in the CPM. Then now what we understood how many objects it can put. now what we're interested is the success probability. So for we imagine this ITSG5 11P technology designed for vehicular communications. So which is based on the CSM-ICA protocol. So then we can do some Markov chain modeling, and then we can calculate the success probability of this technology. So if we see this, compare this when there's only infrastructures transmitting, and one the red case is when everybody is transmitting CPM. Obviously, when there's only one infrastructure transmitting, we wouldn't have problem. There's no collusion, no issue. When everybody is transmitting, with the increase of the density, we will have a performance degradation in terms of the packet delivery ratio. And this we call the channel congestion issue, because there are more and more vehicles transmitting the packets. There will be packet collisions, and then we have this problem. This little up bunch key comes in from the fact that the number of perceived objects jumps from 10 to 6, go back to the 6. So that's why we get up a little bit, but then we degrade again. Yeah. So then now we have we made simulation evaluations also there for the same, basically for the same scenario. What we get in the simulation, we used Wayne simulation, and we have seen that as we expected in theoretical model, that when roadside units sends CPM, the number of perceived objects per CPM almost linearly increase, but for vehicle, it will go up to 10 cars, and that's it. And it cannot put more. But what is interesting is that the effective number of objects in the CPM, what the number of objects that uniquely detected, informed by this vehicle. There, we have only one effective number of objects for vehicle. Even if it detected 10 vehicles, only one vehicle was unique, because the others are the redundant information. So nine objects were redundant. The other vehicles also detected the same object. So this third one is we again confirm the channel congestion issue, that when density increases, the packet delivery ratio decreases. So what we say is that it's reasonable to prioritize infrastructure than a vehicle. So that's what our conclusion. So then what we proposed, and then on the second study is that, okay, we see that we are interested in if roadside unit is providing this CPS service, one thing. Second thing is that if channel congestion is there or not. So we want to based on these two parameters, we want to control the CPM content selection. So the CBR channel busy ratio is measured at the access layer, and if RSU is contributing to CPS, it's basically on the facilities LDM. And yeah, so what we have done. Yeah.
So what is the definition of the channel, and how do you define the probability of success? You alluded to collision, right? So what is the channel, and what are the conditions
so
of success?
In Wi-Fi 11P technology, what we measure is channel busy ratio, and it's kind of knowing that the channel busy ratio has to be around 60 to 70%. This is optimal area. If we exceed, then there's a problem, collusion. So the idea is that we have to keep the CBR between this range. Yeah, that's the card. But it depends on technology. So for 11P, it's not that efficient. So it's maximum 70% it can use the resource. After there will be problem. So for what we have done, first of all, in our system, we say, okay, for vehicle, what we want to do is to control at the vehicle side, because vehicles doing more redundant transmission. Maybe if there's something to control, we have to control at the vehicle. So vehicle, what happens? They have local perception module, okay, with sensors, Then they will select how many objects I detect, and then they will transmit and put it in CPM. That is the basic case. That's the default algorithm. Based on that, what we do is that we have this data fusion module, which gets not only local sensor output, but also the V2X reception. And it will do the data fusion, and it will kind of have this, this table that, okay, who detected what object? Is it vehicle or not? And so on. So it have this, table, okay? So we call it extended perception table. Then based on this table and also channel CBR information coming from access layer, we want to control what object to include, what object not include, or we will send CPM or not. And there we imagine three types of algorithms. First of all, CBR binary and CBR selective look only at the channel congestion. It doesn't care if it's infrastructure or vehicle, or doesn't care. This third one is it will look at channel congestion, channel occupancy, and also if CPM is transmitted, object is detected by infrastructure or not. So the CBR binary is the algorithm that, like I said, it looks at only considers only the channel situation. So what it's doing is that it will look how many objects have been detected only by me. Okay, and if this number of objects is exceeding certain threshold, I will send CPM. If not, I will not send CPM. And this threshold, obviously, based on CBR. We want to keep the CBR between 60–70%. If it's less, then the CBR is less than the 60–70%, then we don't really care. We reduce this threshold, and if the channel is really not congested at all, we can have 0. Let everybody send CPM. But if its channel is congested, then we increase this threshold so that it will be more and more difficult to send CPM for vehicles if there are not many unique objects detected. Okay. Second scenario algorithm is CBR selective algorithm. It's similar, but now we will see how many, because the CBR binary is quite aggressive in the sense that it allows only one redundancy. It doesn't allow redundancy basically. But now we need some level of redundancy. It's quite extreme to say that the doesn't allow any redundancy is not good for safety. So here we allow some redundancy. So it will check is that how many number of, what is the number of occurrences of each object? I detected how many other my neighbors detect the same object. And this number, if this number is below than a certain threshold, I put this object in CPM. And obviously the threshold is again defined by the CBR. Okay, so that part is similar. Third algorithm is CBR and infra-selective algorithm. There, it's very similar to CBR selective, but also the number of occurrences is lower, but also this is not detected by infrastructure. As soon as infrastructure detected, I will not put in my CPM. So that's the difference. So then we made a simulation using six-lane highway with different penetration rate of vehicles and so on. We measured the different three types of metrics. First of all, packet delivery ratio. Second one is awareness rate. Awareness rate is the number of objects, known objects by each vehicle with respect to total number of objects actually exist on the road. So how number of perceived objects compared to real number of objects on the road. Finally, the CBR, channel busy ratio. Objective of this is that PDR we want to increase. CBR, if possible, we want to reduce. Awareness rate, we want to be at least the same level as the default, because default is aggressive algorithm. It sends always. So generally, awareness rate is quite high because it's always informing. So we want to have at least the same level of awareness rate. That's the objective. So first of all, we compare the two CBR-based algorithms, CBR binary and CBR selective, compared to default. So for PDR, we see when the penetration rate increases, we can have almost up to 30% of improvement for PDR. But this is extremely interesting for the CBR CBR selective and infrastructure-based algorithm. We can have almost 100% of PDR, regardless of the density. Second approach is that second thing we measured is the awareness rate. So basically, awareness rate. Good news is that there's not really degrading awareness rate of the system compared to the default algorithm. Almost same. Okay, we're not reducing the awareness rate. Finally, CBR channel busy ratio. All the algorithms on CBR selective and CBR selective infrastructure can reduce the CBR. What was surprising was the CBR binary. We did quite an aggressive algorithm that whether you send or not send, right? Whereas CBR selective, we select the contents, and we expect the CBR binary should reduce CBR, the channel busy ratio, but it's not, because basically CBR selective is reducing the size of the packet size, and that was most impact was higher than just giving up the complete packet. So this is the conclusion so far. So what we got is that we made analytical and simulation study on CPM performances for V2V and I2V communications, and we see that roadside units are quite interesting because it can include up to 8 times more objects compared to vehicles. Effective number of objects per CPM for I2V is linearly increases with the number of perceived objects, but for V2V it can be only 1, whereas it can detect 10 objects, only 1 is effective number. And we made some CPM control algorithms, and performance was good. Okay, so now, okay, good. Okay. Okay, so now we see that okay, infrastructure is quite interesting for perception. And why don't we think further? We talked about perception, so why not infrastructure help on planning part of the vehicle, right? Because infrastructure has higher computing capability. So if it has better perception capability, why not also help in planning parts? So that's the second, we can further think this way. So there are many scenarios we can imagine use cases. So one use case here is that the lane merge, at highway lane merge scenario, where a vehicle is entering to the road and there's other vehicles on the main road. Then we detect, okay, there's a vehicle collective perception. We detect, okay, vehicle is coming, so we ask maybe this vehicle to change the lane. You know, for that we need to do data fusion. We need to collision risk analysis, and then after we give ask the vehicle to change the lane using so-called MCM, maneuver coordination message. This is another type of message which is under standardization. There I will show you a video that we have already testing. We're testing this use case in one of our projects called 5G Mobics. So I have to stop time to time for it to explain. So it's been tested in France, French tri-site. Oh, sorry, I'm not doing. Yes, okay. So what we did. So here we have mobile edge computing system. Okay, we have roadside sensor. We have 3 vehicles in our test. One vehicle is automated car. One vehicle is connected car. One vehicle is basic car. So which means there's no communication capability. And the roadside sensor is basically there to detect all the objects especially VEDECOM. That's what we're interested in to detect. And then all the communication, the roadside sensor will send this information to the MEC. Connected vehicle automated car also send all the count CPM to the MEC. And MEC will do data fusion and analyze the risk. And then if risk is detected, it will ask automated car, in our case, change the lane, okay? So that was that is the scenario. So there is some test preparation. So the first one is basic vehicle, even if we connect with the communication device to have ground truth data. This one is autonomous car, and we have the supervision system. Obviously, the MEC. It will have yeah. Then what happens here? Maybe I need to stop here a little bit there. We have infrastructure cameras to see this situation. Here, autonomous car and connected car is coming, and here basic car will come, okay? And here there's a vision of the autonomous car. So we have already, maybe you haven't noticed, we have already detected collision risk and informed. Sorry about that, it went so fast. Yeah. Here the autonomous car is on the leftmost lane, and then it will be asked to change the lane here. Because we don't see on the screen, but basic vehicle is trying to insert here. So this is all the calculation has been made on the infrastructure side. Infrastructure is data fusion, collision and risk analysis, and so on. Okay. Then now now the supervision system. So the first leftmost, here we have this data fusion output. It will see how many vehicles, what's the objects we have. Then we analyze the collision risk, and then as soon as the collision risk is detected, then we have sent the make sense MCA message. Okay, look, you change the lane to avoid collision. So that's already, well, in our case, it's only 3 vehicles, not too complex, but yeah, it's already working, and I think infrastructure has quite interesting for automated driving. Okay, thank you very much.
Thank you for the nice presentation. Time for questions.
I do have one. Thank you for the presentation. And I have a question on the congestion case on the CPM. So I get it that you find the CPM is long. You have a risk of collision on the channel. And so, yeah, the results that you presented, they make sense. I was wondering if, in your opinion, all of this holds if you switch to V2X, for example. When you have a scheduled transmission. So I know that for a CAM occupies a time slot. I don't know if a CPM can be put on 3 channels and still occupy a time slot, or it has to spill on other time slots. But I was wondering, well, it's not clear to me whether you observe the same dynamics if you change on V2X. So my question is, did you
Yeah, yes. Thank you.
Question? Because it was not audible in the bridge. Resume the question.
Okay, so the question was that the observation we got on for CBR will hold for V2X technology, right? So for CV2, thank you for the question. So for CV2X, there are 2 modes, right? One is mode 3 and one is mode 4. Mode 3 is basically coordinated by infrastructure. So it can be, in my understanding, it can allocate resource in such a way there's almost 100% resource utilization and no collision. So we don't talk, obviously it will not apply there because it's not contention-based algorithm. But CV2X mod 4, yes, it holds. But the 60%, 70% is not, because it's different technology. We need to readjust the range. But CV2X mod 4 is basically carrier sensing mechanism. It's similar, very similar algorithm. Even if there's a 2-dimension to frequency, time dimension, and things are more complex than 802.11. But it will hold because it's still contention-based algorithm. For the slot utilization, it will be more complex. Even if CAM, you say that it's periodic and so on, but in reality, CAM is not exactly periodic, and its size is not exactly fixed. So it's more complex already for CAM, and CPM is more complex because it's also not periodic at all. And also, depending on number of objects, the size can be very different. So most likely it has to be put on different resource blocks and so on. But basically it's contention based, so it's basically this.
And the other thought that I had is that if you use the infrastructure, because you're using, like, the idea is I give a privilege to the infrastructure because it knows better, then why do not let the infrastructure schedule, and then you don't get any collision? Like, it's the infrastructure saying, I will transmit and you shall not.
Yeah, basically what we're doing is that our control is on the facilities layer control, right? So if the infrastructure do the resource allocation, then we're talking about what technology we use.
Yeah, I was just saying that what you are doing here, it could be made easier with CV2X, because you have this native prerogative of the infrastructure of scheduling the users. So
Yes. Obviously, that one thing is that when we use CV2X 3G mod 3, then most likely there's less issue on the collusion, but there will be still limit of the bandwidth. So they will still think, okay, should I still send it? Because there's no more resource available. All the resource has been allocated. Still there's a question remains, right?
Thank you.
More questions?
Maybe a practical question. In the video we saw, what was the exact, what was the frequency of packets that were sent, I mean, to allow for this maneuver every 100 milliseconds, and what was there a sort of tracking of objects? Or,
yes, of course.
and
So
how big were the packets in terms of the bytes?
So okay, there were different types of packets. So CAM, CPM, we follow the standard. So the size varies, okay, and period also varies. But CPM is heaviest one compared to CAM and MCM. But if I remember, I have a graph somewhere. But if I remember well, what in our simple case, CPM went up to 70, 80 bytes. MCM is around 200, 300 bytes. Yeah, only. Yeah, and MCM is generated basically when event is detected. But CAM CPM is generated following the standard. So between 100 millisecond to 1 second. This is the,
More question, maybe if someone online. When you check, I have a question about complexity. So I saw in the video there were big hardwares, maybe it was the screens, but I wonder whether there's a lot of computing complexity behind, or is something that is low level that may be implemented in simple hardware.
I believe in our scenario, so we use the prototype, right? So it's not very.
By definition used.
So, but the processing delay was around 30 milliseconds for the MEC side, for the data fusion, for the risk analysis, and so on. We around 30 milliseconds of processing delay with, I cannot say the spec, the machine I forgot, but it's quite powerful one, but still not the real make industrial thing.
That's
Yeah.
promising in any case. It's not impossible to do this on.
No, I don't think so. It's possible.
Thanks.
Thank you so much.
Anyone from the online floor? No. Then let's thank the speaker again. Thank you very much.